A warm welcome to all. Good morning to everyone. We are honored to present to you of our final year project. We are from Batch 14 Electronics and Communication Department, our final year student of Well-Tech Multitech Dr. Rangarajan, Dr. Saguntala Engineering College. We would like to extend our heartfelt gratitude to our college management, our respected principal sir and head of department Prabhu sir and project coordinator Abbas sir and our guide Mr. Jabasingh sir for the unwavering support and encouragement throughout this journey. Our project titled as Transparent Antenna Based Mesh Sensor Design and Development for Food Quality Monitoring. My team consists of 4 members: S. Inbatamaran, K. Sashwin Kumar, S. Tilakraj, and H. Vishnu Prasad. And we are excited to walk you through the insight and innovation we have incorporated into this project. Let's dive into how we are transformed ideas into reality and executed our vision. Before we move forward, let's discuss the key objective of the project. This project aims to improve food quality monitoring using transparent antenna based sensor. Let's take a look at our main objective. The objective of the project are as follows: to design a transparent mesh antenna sensor for real-time food quality checks, to detect the spoilage sign like moisture and gases wirelessly, to enhance food safety and boost consumer confidence, to integrate sensor into packaging for a better supply chain and less waste. These objectives will help in developing an advanced system for monitoring food quality effectively. Every year, there is one third of the food is produced worldwide goes to waste. Due to undetected spoilage, one of the main reasons is lack of real-time food quality monitoring. So, keep the food fresh and safety is very important. Imagine we had a smart system that could instantly detect the signs and alert the consumer and suppliers. This is exactly our project aims to achieve using transparent mesh antenna for real-time food quality checking. We have discussed the objectives. Let's take a step back and understand why this project is important. What is important of our project? In today's scenario, there is a lot of tools available for various purposes. For example, measuring glucose (BP), we have a glucose meter. For measuring gold, we have a carat meter. But for food quality checking, there is no instrument available for in domestic purpose. That's why we developed the transparent antenna for real-time food quality checking. Food safety is a critical concern in today's world. Contaminated or spoiled food can lead to a serious health risk. This is why the food quality measurement is essential in the food industry. Traditional food quality checks involve manual inspection, which are time consuming, expensive, and sometimes destructive to the product. Our project focuses on mitigating the risk of foodborne illness through advanced detection method. It ensures consumer safety, regulatory compliance, and brand reputation while maintaining the integrity of food product. The use of transparent antenna sensor allow real-time wireless and non-invasive food quality measurement. In short, our project provides a modern, effective solution to enhance food safety without altering the product. This can revolutionize the food industry by making quality check faster, safer, and more reliable. The system enables a real-time monitoring of food quality using transparent and flexible mesh sensor. It detects the spoilage indicator like gas emission and temperature changes effectively. The transparent design ensures seamless integration into food packaging without compromising aesthetic or safety. Wireless communication allow easy data transmission to mobile apps or dashboards. By providing timely alerts on food freshness, the safety helps reduce food waste and ensures safe consumption. It also improves efficiency in storage, transportation, and retail environments. The innovative solution addresses the industry challenge with a cost effective, scalable design, enhanced safety, and consumer trust in food quality monitoring. Before starting our project, we conducted a literature survey to understand the existing technology and research in the areas related to transparent antenna and food quality monitoring system. The primary focus was to explore current method used in the food quality assessment and how antenna technologies specifically transparent antenna can be integrated into the system. This survey provides insight into various advancements in wireless communication, sensor network, and food safety technology. By reviewing the studies, we aim to identify gaps in the current method and highlight opportunity for innovation in food quality checking through transparent antenna-based solution. RFID, radio frequency identification technology, combined with antenna, is commonly used to track food product during transportation and storage. RFID tags store information like temperature and expiry dates, which can be read wirelessly. The system helps monitor food quality in real time and preventing spoilage and ensuring safety. RFID and antenna are already widely used in food supply chain to improve food safety and efficiency. Thank you. The transparent antenna are made from material that allow light to pass through while still working as antennas. These are used in applications like smart windows and displays. When combined with sensor technology, transparent antenna can help monitor food quality by transmitting data about things like temperature and moisture. This approach can improve food safety while keeping the packaging or system visually unobtrusive. To start a section on flexible antenna in our project. Flexible antenna are widely used in wearable devices like fitness tracker and health monitor. These antenna are lightweight and can bend without losing performance. Research shows that flexible antenna work well for devices that need to transmit data continuously while remaining comfortable for user. This makes them ideal for application where the flexible and easy of use are important, similar to how our antenna technology can be used in the food quality monitoring. This block diagram represents the initial idea of our project. Let me walk you through the antenna testing process, which plays a crucial role in determining the quality of the packed food sample. We start with the food sample and use a transparent antenna to detect how the food interacts with the electromagnetic waves. The antenna collects the data from the food sample and sends it to the VNA vector network analyzer. The VNA measures how much of the signal is reflected back by the food through return loss. A higher return loss indicates a greater impedance mismatch, which can be correlated to certain quality or spoilage level in the food. By analyzing the return loss data, we can estimate the food spoilage value, helping us determining if the food is still fresh or if it has started to degrade. This data feeds into a larger quality analysis system, which is further processed using machine learning models and statistical method to provide a final food quality assessment. This block diagram and flow will give you audiences a clear structure, understanding how our antenna testing contributes to food quality determinations. Block diagram for MATLAB implementation with elaboration. The starting point of the system, this is food sample that will be tested for quality. The food is analyzed to check for spoilage or other quality factor. The key component that captures data from the packed food, the transparent antenna, works by detecting electromagnetic signal from the food without interfering with the sample itself. The antenna collects the data in the form of electromagnetic waves or signal from the food. This is essential for understanding the quality of the food. The data acquisition unit collects the signal and convert into raw data from the transparent antenna. It ensures that the captured signal are ready for further processing and analysis. The data acquisition converts the signal into usable format for processing the includes amplifying or converting the signal into digital format. After data acquisition, the data is filtered using SWT stationary wavelet transform and DWT discrete wavelet transform. This wavelet transform are applied to remove unwanted noise and highlight the most important features of the signal. These steps ensure the data is clean and relevant for analysis. The filtered data passed to the neural network, a machine learning model that identifies the pattern and a relationship in the data. The neural network analyzes the process, learning patterns that relate to the quality of the food. It classifies the food as either fresh, spoiled, or of another quality. The output of the neural network is converted into a statistical value that represents the food quality. This value can be score or classification. The value qualifies the food quality and prepares the result for easy interpretation. Block diagram for hardware implementation. the food sample that will be tested. It's starting point for your testing system. The filter cleans the process, the raw signal from the food, ensuring that the only relevant and clean data moves forward for analysis. A microcontroller is used to process the filtered data. It could be Arduino, Raspberry Pi, or any other similar microcontroller that receives input data, applies logic, and determines how the system processed based on the received signal. This module is responsible for determining whether the food is good quality or has gone bad. It analyzes the processed data potential based on parameters such as reflectivity, moisture, etc., and makes a determination. The cloud service as a storage and analysis system where the food quality results are uploaded. This allows for remote monitoring and further analysis, make the system scalable. The substrate used in the proposed system is Artidoride 5080 with a dielectric constant of 2.1 and thickness is 0.5 mm. Thick substrate constitute for better performance. The substrate is placed on the axis by selecting the box and entering the desired value of the length and width 43 mm, and the ground is 2D planar structure that forms a bottom layer of the transparent antenna. It is used for the protection of the patch from reflection. The dimension of the ground are the same as that for the substrate. The ground is placed in the axis by selecting the rectangular symbol and entering the value of the length and width as per our design consideration. The length of the ground is 43 mm, the width of the ground is 43 mm. The shape of the patch used here in the circular shaped patch is most commonly used among different shapes because it produces a linear polarization and also easy to fabricate. It produces a low cross polarization. The microstrip patch antenna fed by the microstrip feed, the inner conductor extend up the patch through the substrate and soldered to the metallic paste. Design of transparent antenna. Due to high cost of orthodurite substrate, due to their small size, lightweight and simple construction, a micropatch antenna have seen widespread application in recent years. An oval microstrip patch antenna that makes uses of electromagnetic wave band structure is suggested as mean of enhancing the antenna performance. The dielectric constant of the substrate. The dielectric material chosen is orthodurite 5080 Tm, which has a dielectric constant of 2.1. To reduce the dimension of the antenna and to obtain better performance, the value of dielectric constant is chosen to be high. The best height chosen for orthodurite TM substrate is 1.6 mm for the designing transparent antenna. This will be prevent the generation of surface wave which result in loss. The width of the W of the patch is very important. It controls the input impedance of the antenna. For typically square shape antenna L equal to W, the input impedance is typically 300 ohm. When a width is increased, the input impedance decrease. The width is not only control the input impedance but also control the radiation pattern of the patch antenna. The effective dielectric constant of the rectangular microstrip patch antenna is calculated as h equal to height of the substrate, mu r equal to dielectric constant of the substrate. Result and discussion. In our proposed work, after simulation is completed, the HFSS file is exported and is saved as a AutoCAD DXF file, which is further given to the fabrication center for the fabrication of PCB. Then a SMA connector is soldered to the fabricated PCB. The fabricated antenna is shown below. The return loss is the loss of power in the signal as equation 1, which gets reflected due to discontinuity present in the transmission line and expressed in decibels dB. The fabricated design achieves a return loss of minus 40.09 dB at operating frequency of 2.70 GHz with a VSWR of 1.201 at the same frequency. Within this, the range there is a minimal signals providing an optimized sensing point suitable for food quality measurement. The final result of our IoT based food quality detection system as visualized on the ThinkSpeak platform clearly demonstrates the effectiveness of our approach in distinguish between good and bad food samples. The plotted graph reveals two distinct patterns: stable grounded points and sharp spikes. The grounded points correspond to food samples, indicating stable and consistent sensor reading, while the spiked plots represent the bad food samples, signifying anomalies in the sample of due to contamination, spoilage, or food quality parameter. The project is successfully demonstrated a practical and scalable and cost-effective approach for food quality assessment using IoT, MATLAB, and simulation. This MATLAB scripts implementing an adaptive neurofuse interference system for time series prediction. It starts by loading a time series dataset from a file and processing by using delay embedding approach where past values serve as input to predict future values. The dataset is then divided into training and testing sets. The scripts allow the user to choose the method for generating a fuzzy interference system, offering three options: grid partitioning, substantive clustering, and fuzzy. Based on the selection, the user provides a parameter such as number of membership function or clustering radius. The selected method initializes FIS model for training. Performance evaluation of neural network model for training testing and combined dataset. The given representation plot illustrates the performance of adaptive neurofuse interference system in predicting target the value based on training and test data. The top left plot represents the training data where the correlation coefficient is 0.84338, indicating a strong correlation between the predicted and actual values. The blue regression line follows the equation output 0.7 into target plus 25, showing that the model fits the training data well. The top right plot, representing the test data, has a lower correlation coefficient, or equal to 0.38173. It indicates the poor generalization to unseen data. The regression equation output equal to 0.38 into target plus 53. It shows a weaker relationship with prediction deviation more from actual value. The bottom plot, which includes both training and test data, it moderate correlation coefficient R equal to 0.7007, which regression equation output equal to 0.62 into target plus 32. This suggests that while model perform reasonably overall, its weak test performing points to overfitting. To improve generalization, adjustments such as reducing model complexity, incorporating more diverse training data, optimizing training parameter, or select different FIS generation method could be considered. Our project, the transparent antenna based mesh sensor for real-time food quality checking, aims to provide a smart and efficient solution for monitoring food freshness. The hardware setup includes Node MCU microcontroller, a gas sensor, and a transparent antenna based substrate. The microcontroller processor the sensor data and transmit to cloud for real-time monitoring. The workflow follows a structured block diagram where a food emits certain gases, which is filtered and detected by the sensor. The microcontroller programmed with Arduino code reads the sensor data and sends it to ThinkSpeak cloud platform, where the data is visualized for analysis. The Arduino code plays a crucial role in the system. It utilizes the ESP8266 Wi-Fi module to establish connection with Wi-Fi network and communicating with ThinkSpeak using its API. The gas sensor, connected to A0 pin of the Node MCU, continuously measures the gas concentration in the surrounding environment. The analog readings are captured and displayed on serial monitor for debugging purpose. The data is transmitted to ThinkSpeak at regular intervals, allowing for real-time observation of food quality parameter. The ThinkSpeak graph in the slide represents the variation in the sensor reading over time, indicating the change in the food freshness. As food starts to degrade, the concentration of emitted gases increases, which is reflected as a peak in the graph. The real-time monitoring system can be used in industries, households, and storage facilities to prevent food waste and ensure quality control. The transparent antenna based sensor offers a cost effective and efficient alternative to traditional food quality detection method, which integrate to the IoT. The system ensures continuous monitoring and data analysis, make it practical solution for food safety application. Advantages: improved food safety, detect and reject low quality or contaminated food in real time, reducing health risk. Seamlessly integrate without blocking visibility, make it more adaptable. Automated detection, minimize human errors and speed up processing. Reduce labor cost and save time and consume less power. Wireless monitoring enables remote tracking of food quality and enhancing convenience and control. This keep it conscious while still highlighting the key benefit effectively. Application of our project. Our project is useful in food quality inspection, ensuring contaminated or spoiled food is detected in real time. It can be integrated into smart packaging and retail industries for automated quality checks. In healthcare, it enables transparent wireless monitoring system. Additionally, it supports IoT and smart device, enhance real-time data transmission for better efficiency and accuracy. The future scope of this project includes enhancing sensor sensitivity to detect the wide range of gases, integrating temperature and humidity monitoring, and using machine learning to predict spoilage trends. The system can be miniatured for packaging application and expand into a mobile app for real-time monitoring. In large scale use, it can be accumulate food storage management in supermarkets and warehouses and reduce the waste and ensuring food safety. With further development, this technology can revolutionize the food quality monitoring and preservation.